Hello, in this video we're going to talk about rules for significant figures. Right, so first let's go ahead and look at what significant figures are. So you probably have not heard of significant figures in math before, and that's just because in math we assume that unless we're using any kind of measuring devices, the number of significant figures is infinite. But if we are using measuring devices, then the number of significant figures tells us about the precision of the number. So it's sort of like the error in our measurement. So let's look at what numbers are considered significant. Any non-zero digit is considered significant. So for example, the number 25 has two significant figures. The number 436 has three significant figures, and the number 56 grams has two significant figures. Notice that here, the only one that actually has a unit is 56 grams, which indicates to me that there was a measuring device, right, like a scale involved to make the measurement. If there's no unit shown, you assume that it was a measuring device that was used. And so the significant figures are limited to whatever numbers we are given. Another rule for significant figures is that zeros between significant numbers are considered significant. So we know the rule for non-zero digits. The rules for zeros is a little bit different. If the zeros are between two significant figures, then we consider those zeros significant. For example, the zero in the number 205 is significant, so that number has three significant figures. Both of those zeros in the number 4003 are considered significant, so that number has four significant figures. And the number 70,003, so 70003, has five significant figures, so all those three zeros are considered significant. So as long as the zeros are sandwiched between two significant figures, they're considered significant. And those zeros do not have to be directly next to the zero. They could just be anywhere on the left and anywhere on the right side. The next rule for numbers that are considered significant are zeros at the end of a number. Now, at the end of a number, if a decimal point is shown, and only if a decimal point is shown, those zeros are considered significant. It doesn't matter where that decimal point is in the number. It could be before the zero, it could be after the zero, it could be at the very beginning of the number. As long as there is a decimal point in the number, the zeros at the end of the number are considered significant. So for example, the number 20 point has two significant figures, so that zero at the end is considered significant. The number 4.0 has two significant figures. The number 0.70 has two significant figures also. And the number 8.00 has three significant figures. So at the end of a number, as long as there is a decimal point shown, the zero is considered significant, okay, or the zeros. So between numbers that are significant, zeros are significant. At the end of a number, if a decimal point is shown, the zeros are significant as well. Numbers that are not considered significant are zeros at the beginning of a number. If there's any zero at the beginning of a number, whether or not there's a decimal point shown, that zero or those zeros are not considered significant. So the number 025 only has two significant figures, so only the 2 and the 5 are considered significant. The number 004 only has one significant figure. The zeros are not considered significant. The number 0.04 only has one significant figure, and the number 04.1 has two significant figures. So in all of these examples, you can see that the zeros at the beginning of the number are not considered significant, regardless of whether or not a decimal point is shown. The next rule for numbers that are not considered significant is zeros at the end of a number if there is no decimal point shown. The number 250, for example, if there is no decimal point shown, is assumed to have two significant figures. Okay? That number is ambiguous in terms of the number of significant figures that it has because that zero at the end is a placeholder, but it may also be significant. We don't know if it's significant or not, right? It needs to be there to make our number 250 rather than 25. But whether or not that zero is significant, we don't know. And that's where the ambiguity comes in. If there was a decimal point there, then we would know for sure that that zero is significant. But if there is no decimal point shown, we assume that that zero is not significant. Okay, so that number is ambiguous, and we assume that there's just two significant figures. Same with the number 400, 400. If there is no decimal point shown, then those zeros at the end are assumed to be not significant. Okay, it's ambiguous, meaning we don't know if they're significant or not. We just assume that they're not significant. So that number only has one significant figure, and that's the 4. The zeros there are placeholders. They're there to make the number 400 rather than 4. But we don't know whether or not they're significant, so we assume that they are not. Now, there are also numbers that have infinite significant figures. One is numbers that are within conversions in either the English system or the international system. So in the international system, for example, the conversion 1 meter equals 1,000 millimeters. Those numbers, the 1 and the 1,000, contain infinite significant figures. Okay. We assume they have infinite significant figures when we are doing calculations and converting from one unit to another unit. So we don't consider their significant figures in calculation. Okay. We assume that they're exact numbers and have infinite significant figures. In the English system, an example is 12 inches equals 1 foot. There is exactly 12 inches in exactly 1 foot. So that conversion contains infinite significant figures, meaning if we're, let's say, converting from inches to feet, the conversion factors we're using has no effect on the number of significant figures that our answer will have. Another number that contain infinite significant figures are per and percent. If I say, for example, I drove to school at a speed of 45 miles per hour, the per means exactly 1 hour. Now, the 45 there only has two significant figures, right? Because it's 45 miles and a measuring device had to be used to measure the 45 miles. But the per hour means per exactly 1 hour. So the 1 hour in that per hour contains infinite significant figures. Also percent, if I say 35%, percent means exactly 100. So the 35 would only contain two significant figures, but the percent part of it, which means per 100, that 100 contains infinite significant figures. And then the last thing that contains infinite number of significant figures is counting numbers. Counting numbers are numbers that don't require a measuring device they just require counting. No measuring device is needed. So if I say that there are 56 students enrolled in this class, I did not need a measuring device to figure out how many students were enrolled in the class. I counted 56 students. And students are whole things, right? I can't have 56.2 students enrolled in the class. So that contains exactly 56 students, so that contains infinite significant figures. So things that can be counted contain infinite significant figures, and those are things that can't have parts. Another would be 12 dots. You can count dots, right? So those contain infinite significant figures because you don't need a measuring device for them. All right, so what are the rules for significant figures in multiplication and division? So let's say you're multiplying two numbers by each other, or you're dividing two numbers by each other, and you want to know how many significant figures your final answer will have. The rule is that the answer has the same number of significant figures as the number with the least number of significant figures. So here's an example. If I have 12 divided by 2.00, 12 has two significant figures. 2.00 has three significant figures, right? It has three significant figures because those zeros count since there's a decimal point there. That means my final answer should only have two significant figures. The reason it would only have two significant figures is because the 12 has two significant figures, and that's less than the three significant figures of the 2.00. So my final answer has the same number of significant figures as the number with the least number of significant figures. In this case, 2. Here's another example. If I multiply 60.0 by 2.0, notice that 60.0 has three significant figures. The zeros at the end count because there's a decimal point in the number. 2.0 only has two significant figures. So my final answer should just have two significant figures. Because I don't have a decimal point at the end, then this number is assumed to just have two significant figures. So 120 has two significant figures. The zero at the end is just the placeholder. A better way to write this number would be to put it in scientific notation as 1.2 times 10 squared. That'll more clearly indicate that there's only two significant figures in that number. And then here's a third example, similar to the one above, except here it's 60.0 times 2.00. Notice that both of those numbers have three significant figures, which means that my answer would also have three significant figures because the least is 3. So in this case, I put a decimal point at the end after the 0 to indicate that that 0 is not only a placeholder, but also a significant figure. So this number here, 120 point, has three significant figures, whereas up here, 120 without the decimal point only is assumed to have two significant figures. All right, now let's look at the rules for addition and subtraction. The rules for addition and subtraction are a little bit different than multiplication and division. Remember, with multiplication and division, the rule was that the answer has the same number of significant figures as the number with the least number of significant figures. For addition and subtraction, the rule is that the answer has the same number of decimal places, not significant figures, but decimal places as the number with the least number of decimal places. So when we look at decimal places, we look at the numbers before or after decimal, the very last digit, and where that digit is relative to the decimal point. If there's no decimal point shown, we just assume that it's all the way at the end of the number, except if the digit at the end is a 0. So here, we have only one place after the decimal. 12.5 has one place after decimal. 3.00 has two places after decimal. So when I subtract these two numbers by each other, my final answer should just have one place after decimal. because the number with the least number of decimal places, which in this case is the 12.5, only has one place after decimal, that determines how many places after decimal our final answer will have. Okay? Notice it has nothing to do with significant figures. Each of my numbers here, 12.5 and 3.00, have 3 significant figures, but my final answer only has 2 significant figures. So the answer, the final answer, how many significant figures it has, is not determined by the number of significant figures, but by the decimal places. Okay, so when we're subtracting or adding, we look at decimal places. And here's another example. 10.000 has 3 places after decimal minus 0.05. This number has 2 places after decimal. My final answer should have the same number of places after the decimal as the number carrying the least places. So my final answer would also have just 2 places after the decimal, just like this 0.05. Again, it has nothing to do with significant figures. This number has 5 significant figures. Okay, this number only has 1 significant figure, just the 5, because the zeros before don't count as significant figures. But my final answer has 3 significant figures, right? So we're not looking at significant figures to determine the number of significant figures at the end when we're adding or subtracting. We look at decimal places. 2 places for my final answer, because the number with the least decimal places only had 2 places. And then just one more example. So 6.2 plus 93.8. Notice that 6.2 only has 1 place after decimal. 93.8 also has 1 place after decimal. So my final answer should just have 1 place after the decimal. If this calculator doesn't give it to you, that number after decimal, which in this case it will not, when you put this in the calculator would just give you 100. You will yourself have to add that 0.0 at the end to show the correct number of significant figures. Okay, your final answer should have 1 place after decimal, so you have to put the 0.0 there. If you don't put the decimal point or the 0 there, then it will not be correct, and it would just show 1 significant figures. Okay, so don't forget that. So last, what we're going to look at is solving problems that involve multiple operations. Notice that in this problem here, I have multiplication, subtraction, parentheses, exponents. So how do I know what to solve first, and how do I know how many significant figures my answer will have at the end? So in math, you may have learned PEMDAS, which tells us the order of operations. So P stands for parentheses, which means that we first solve whatever is in parentheses. We don't necessarily start from the left side of the equation. We have to take into account the order of operation. So parentheses first, then exponents, then multiplication or division, and this would be from left to right, or if there's more than one multiplication or division problems. And then last is addition and subtraction from left to right. So to solve this problem here, I'm not going to start off with the 25.6. I'm going to start off with the parentheses. So first, what I'm going to do is take the 3.42 minus 6.51. So I'm first going to solve this over here. When I subtract those two from each other, so 3.42 minus 6.51, the calculator gives me negative 3.09. Now, for significant figures, I do not round until the very, very end, but at every step, I keep track of it. So here, I'm subtracting, so I apply the subtraction rule for significant figures, which is decimal places. I have 2 places after decimal here, 2 places after decimal here, so I would have 1, 2 places after decimal here as well. So I keep track of it, but I will not round. Okay, so I'm done with the parentheses. The next is exponents. So here I have exponents. I have 3.61 squared. So when I multiply these two, or 3.61, when I square it, the calculator gives me 13.0321. Because exponents are like multiplication, I apply the multiplication rule, which is significant figures. This number here has 3 significant figures, which means my answer should have 1, 2, 3 significant figures. So it would be under the 0. Again, I do not round until the very end. So I keep the rest of the numbers, the 3, 2, and the 1, until at the very end when I'm ready to round. You don't need to carry like 3 numbers after where the cutoff should be, but it should be at least 1 or 2 numbers that you should carry beyond where the cutoff is. So these two would be added here. Then the next operation is multiplication or division. So I'm going to multiply these two numbers by each other. So I have 6.812 times 3.48. Okay, when I multiply these two by each other, the calculator gives me 23.7058. And then when I apply the rules, it's the multiplication rule for significant figures, which is number of significant figures. I have 3 sig figs here, 4 here. I go with the least number of significant figures, which is 3. So 1, 2, 3. The cutoff would be at the 7. So this is a minus here. And then the last order of operation I have is the addition and the subtraction from left to right. So I'm going to add and subtract all of these numbers from each other to get the final answer. So 25.6 plus 23.7058 minus negative. Minus negative is the same thing as plus. So plus 3.09 plus 13.0321. And when I put this in the calculator gives me 65.4279. Because the last order of operation I did was addition and subtraction, I apply the significant figure rule for addition and subtraction, which is looking at the least number of decimal places. So this number has 1 after decimal. This was 1 after decimal. Remember, I do not look at the 0, 5, and 8. I don't round them until the end, but I look at where I drew the line. This number has 2 after decimal, and this has a 1 after decimal. The least number of decimal places is 1, so my final answer should have 1 after the decimal. I draw the line here. Since this is a 2, the 4 stays as a 4, so my final answer would be 65.4. Okay, and that would be it. That would be the answer that I would get here. All right, so we've reached the end of this lesson. Here are just some practice problems on this lesson for you to do off by yourself. So go ahead and pause the video, do these problems, and then the answers are going to be on the next slide. And here are the answers to those problems.